In this video, we want to show if the invariant holds and the guard holds, that once we perform the command inside of the while loop, we end up in a state satisfying the invariant, which means we need to show that the invariant and the guard imply the weakest precondition of the command inside of the while loop invariant. How do we do this? Well, first, let's instantiate the command inside of the loop invariant, and notice that the command inside of the loop is actually the sequential composition of two commands. And so if we want to find the weakest precondition of that sequential composition, we know the post condition for the first command is the weakest precondition of the second command invariant. But that second command is an assignment where k becomes k plus 1. So everywhere in the invariant we find a k, we do a textual substitution of k plus 1. And that leads us to a quantification where I ranges from 0 to k plus 1, and an interval where 0 is less than or equal to k plus 1 is less than or equal to n. If we look at this quantification a little more, we will notice that the range is that 0 is less than or equal to I is less than k plus 1, which we could write as 0 is less than or equal to I is less than or equal to k. And since I want to do an update on ck, what I think I'd like to do is to use splitting the range of the quantifier here before I look at the weakest precondition. And so what I'll do is I'll write this quantification as for all I between 0 and less than k, ci is equal to ai plus bi, and when I is equal to k, ck is equal to ak plus bk. So now when I do the textual substitution, ck becomes ak plus bk. What I'm going to do is do a textual substitution for ck, ak plus bk, because I'm trying to find the weakest precondition of an assignment. I find that I have the quantifier and ak plus bk is equal to ak plus bk and an interval. Now let's look at this. ak plus bk equal to ak plus bk is true. Any expression and true is the expression. In addition, what I can do is rewrite this interval. If 0 is less than or equal to k plus 1 is less than or equal to n, I can change the interval to describe the range of k. That would mean the k would have to be greater than or equal to -1 and less than or equal to n minus 1. But being less than or equal to n minus 1 is equivalent to being less than n. So my predicate actually simplifies to the invariant and the guard imply this quantification, and -1 is less than or equal to k is less than n. Let's instantiate now for the invariant and the guard. Now notice that both the invariant and the guard have intervals that tell us the range of k. Well, according to the invariant, k is between 0 and n including n, and the guard says it's strictly less than n. If I use associativity and then perform arithmetic, I can rewrite that as k is between 0 and not including n. That I also can look at the interval -1 is less than or equal to k less than n and rewrite that as either k is equal to -1 or it's between 0 and not including n. Then what I can do is I can distribute the quantifier through this OR statement that I just created. Now why did I do all of this? Because if I stare at what I have on the left-hand side and what I have on the right-hand side of this implication, there's a lot they have in common. And the stuff that's left over on the right-hand side is or stuff, which means that by weakening and strengthening, I know that my predicate is true. And so I have just shown that after an iteration, we are in a state satisfying the invariant again. Of course, that means by inductive hypothesis and an inductive proof, if we started in a state satisfying the invariant, and when we iterate, we end up in a state satisfying the invariant, every time we iterate, we end up in a state satisfying the invariant. So, this will help prove partial correctness of the loop.